of a series expanding space research through collaboration. And today we have the great honor of a visitor from University of Bordeaux, Thierry Stoecklin. How do I say it? Sorry, I should have asked you before.
It's good. It's good.
Thierry holds a PhD in chemical physics from the University of Bordeaux. And he's very interested in the chemistry of interstellar clouds and also planetary atmospheres. The science that he works on also applies to cooling and trapping of cold molecules. And to do all these investigations, he uses quantum dynamics. And today he will be speaking about the role of vibrational excited water in evolved stars or star-forming regions. Welcome to FSI.
Thank you. And also thank you to Slava, who gave me this opportunity to visit you and to speak today. So we started collaborating some years ago now. I will not say how many, and so I will speak. So it's possibly a bit oversold, I would say, the title, because I will not answer to the question which is in the title. I will rather ask you an answer to this question. So it is part of the Water Stars project, which is a project from the French National Agency of Research, which is dedicated to the vibration of water. And it gathered an experimentalist group, the group of Astrid Berger in Bordeaux, who has a cross-beam experiment, some astronomers also from the lab in Bordeaux, which is a laboratory of astronomy, and also another group in Grenoble with Alexandre Faure and people also who are working on modeling interstellar clouds. So,
It
no, I
online
don't
looks well.
want to lead the meeting. Okay. So within the project, we are supposed to work on the collision, of course, of water with the most abundant collider in the ISM, so which you all know. And I have added also some other collider which are not of very strong astronomical interest, argon or neon, simply because in the experiment, they are used in Bordeaux to test the experiment. So, of course, to provide some also some calculation may be useful. So the name of the people who are involved, Ricardo is the PhD student who has been working during the course of the project, and Otoniel Denis Alpizar is a colleague in Chile who has provided mainly the potential energy surface, and Alexandre Faure, who is an astronomer who is in Grenoble. So, in fact, the real title I can tell you now, today, of my talk is the bending relaxation of water by collision with para and ortho H2. So, this is the cover of one of the last issue of the journal ChemPhysChem. So, of course, I do a bit of advertisement, but also I know that in your community, you don't know the journal, and you will never look at papers, I think, in this journal, probably. So you may have a look. There are some chemical physics papers which are of interest for the community, I think. So the water detection, as you know, is a real problem because of the atmospheric opacity. Here it is represented on this slide with the radio and the infrared opacity. But it is really ubiquitous, and the spectrum richness is the greatest in extended atmosphere and envelope of oxygen rich stars of our galaxy. And the winds coming from this region are the main providers of chemical enriched gas and dust particles the ISM. So the first infrared low spectral resolution detection were made already in 1964. And then more recently, if I can say, in 1969, there was some higher resolution detection made, but in the radio. So the three normal modes of water are represented there. And in fact, within the Atomium ALMA project, so which was made by many people, and one of the main contributors is Alain Baudry from Bordeaux. And this is the reason, in fact, of our project, because they detected in the course of this project 7 very high energy transition of water between 4,000 and 9,000 K, and well above the transition which were detected before. And one of these transition, which is inside the doubly excited bending mode of water at 268 gigahertz, seems to be widespread. So here are the transitions which have been detected during the Atomium project. So in blue and in yellow, I'm not sure that you can see anything. In fact, I'm sorry about that, because I have difficulties myself to read it, so suppose you cannot. So you have transition without any change of the vibrational states of the rotation, and they are the one in blue. And the one in yellow, of course, are the one with change of the vibrational initial and final state. So as you can see, in principle, if we want to represent that, we should calculate and also experimentally measure cross-section for all these transitions, which mean with change of vibrational and rotational states. So it's a lot of work, and for the collision of H2O with water, we choose first to have a look at the bend only relaxation, so bending relaxation within the rigid bender approach. So there are almost non-experimental results for vibrational relaxation. Here, for this system, we have only one measurement at 300 K for the bending relaxation. And we will see the comparison with this data at the end of the talk. And on the theoretical point of view, there are many rigid rotor calculations available, since the early work of Green. And you may know also the work of Duvernay et al., who did a lot of calculation. There were some quasi-classical trajectory calculations, which were made quite early, I have to say, by the team of Pierre Valiron in Grenoble, it's for et al. And they included the quenching. And the first quantum results were obtained by Wiesenfeld in 2021. But in his approach, it doesn't include the coupling between bending and rotation, and we will see that there are limitations to this approach. So if we want to do such scattering calculations, the first thing, of course, is to obtain the water bound states. So the water bound states are calculated using an Hamiltonian expressed in Hadot coordinates. And it is which is diagonalized in the basis set describing the two radial vibrator, the angular vibrator, and the rotation of water. And we use the potential of Bocazatel, which was published quite recently, which is the best potential for water existing at the moment, I think. And we, in fact, use our own made code. As you know, there is a code which was developed long ago by Tennyson, which is called DVR3D, and which allows also to calculate bond state for 3 atom systems. But it doesn't allow to get the bond state wave function that we need for the scattering calculation. And also we wanted to try it ourselves, so that's what we did. And we use, in fact, our approach is slightly different from the one of Tennyson, as the DVRs that we use are slightly different. And in fact, this Boston-Sosmor's potential optimized DVR is very powerful and was used by another team recently, which gave us, by the team of Young et al., by the way, which gave us this idea to use it. So here are the comparison between the results and our calculation for the bond state energy of water. So in blue, that's the difference between experiment and our calculation. And in yellow, it is the calculation of Young et al., which have some subtle difference also with our approach. And we were quite happy to see that. So here it is for para water, and here it is for ortho water. And it is the last column here. And you see that we are 1 order of magnitude closer to experiment than this calculation from which are quite recent. So we are very happy about it. And then we need to perform the calculation, the scattering calculation, so that we do in the space-fixed frame. And so the usual close coupling equation are this one for the radial part. And here, this matrix element are the matrix element of the potential, which are, you can see, a product of the rotational part and the vibrational part. So that means that rotation and vibration here in this equation are strictly coupled. They are not uncoupled. And we use here an 8D restriction of the 9D potential of Valliron et al. But what I will show you will not include the transition between stretching levels. It's only transition between bending levels of water due to the collision with para and ortho H2. We can first have a look at the rotational condition inside a given bending level. So here we consider the fundamental level, mu2 equals 0, and the first excited one, mu2 equals 1. So we consider the collision with para H2, and we start from the initial level, rotational level of water, 2 to 0. And what is represented here, this number, it is the final state of water. So the first number is the final vibrational bending state of water. And J can see the usual notation for the rotational state. The solid line are for the condition inside the excited bending level of water, and the dashed one inside the fundamental bending level. And as you can see, there are differences, but not many. The resonance position are about the same for almost the transition. The part at very low collision energy, because there are some subtle difference of the long-range potential in this case. And but what is really noticeable is that the magnitudes are slightly lower in the excited mu2 equal 1 level. For example, you can see it here. And it is due to the fact that some channel associated with excited level of H2, J2 equal 4, which are open in the excited level. And interspersed between open U2 equal 1 levels. So of course, part of the flux, is going into these channels and reducing the flux in the other channel, which makes that the cross-section are a bit lower. So now, again, a slide that nobody can read. That's always good. So we consider now the bending relaxation propensity rules for para H2 colliding with or para or orthostate of water. So here, that's the para state of water, and here the orthostate of water. And unfortunately, you cannot really see, but what is done is the number which are represented here are corresponding to the level of the final level of H2, not water. It is summed over all the transition of water for bending relaxation. And what is and in light blue also there is here on one curve we have put some rotationally elastic cross section inside U2 equal 1, which is you see quite above. So I think you will have to trust me rather than to see it on the curve. I'm sorry about that. So all the channels of H2 equal 0, 2, and 4 are open and give contribution in ascending order. And the global bending relaxation cross-section are, in fact, almost equal to the transition to J2 equal 4, which gives the largest contribution. And it is completely in contrast with rotational relaxation. As you know, rotational relaxation favors the lowest delta J, which means the difference between the initial and rotational, the final rotational level. And this is simply because vibrational relaxation is controlled by a near-resonant energy transfer mechanism. The largest contribution is provided by the final internal levels of the complex, which are the closest in energy with the initial level. It's a very simple rule. So what I showed you is a blue curve also that we have seen there, corresponding to rotationally inelastic collision, pure rotationally inelastic collision, deep cross-section which are increasing with collision energy and up to 5 orders of magnitude larger than bending relaxation. That's the usual ratios that we find between vibrational relaxation and rotational relaxation. So now we can do the same for the collision with ortho H2. And again, you have the parastate of water on this side and the orthostates on the other. And what you can see is that there is a real difference. So in fact, here it is the final level of H2 is 1, 3, 5. And it's completely different from what we had before. So here you see it was completely regular, and you had 0, 2, 0, 2, 4. And all the curves were the same. Here we have 5, which is opening at higher energy. It is not open at low energy for some initial state of water. So this is exactly that. J2 equal 5 is closed at low collision energy for the initial channel level. And the main contribution to bending relaxation is then due now to J2 equal 3. I'm still speaking about the state of H2 for almost all the initial level represented. And contribution of the J2 equal 5 final level, exhibit many resonance, which is logical as it is the closest in energy with initial level and consequently most sensitive to the opening of rotational levels. So inside water, so you see all this resonance there. So now we may have a look also at the impact of the initial water rotational excitation. And here for the collision with ortho H2, and here for the collision with para H2. So at low temperature, you can see, so you can probably not see very well also. Here it is J equals 0, J equals 1, J, if you give myself, I have to look at the screen, I'm sorry. J equals 2 and J equals 3. And here the Boltzmann average rate. And here it is the same, 0, 1, 2, 3, and Boltzmann average. So at low temperature, the J equals 0 quenching rate increase as a function of temperature for the collision with ortho H2. So here it is this curve, okay? And it decreases for the collision with para H2. So here it is this curve. At higher temperature, for both collisions with para H2 and ortho H2, the J equals 1 quenching rate becomes larger than J equals 0. You can see it there. And now, if we want to compare with experiment, so the initial Boltzmann average ortho H2 contribution is negligible below 30K. So it's not, of course, probably visible from the curve because here we have put separately the different contribution and the Boltzmann average is this one, which is like that. Okay, so you see that the global rate coefficient, which is there, the contribution of J equals 1, here at 30K, around 30K, you see that there is a difference. It slightly increases and becomes significant above 100K. So, and now if we compare our calculation with the only data available, experimental data available, our value is 118 10 minus 12, and the experiment is 103 10 minus 12, which is not bad. So before ending this study, we also had a look at the bending rotation decoupling approximation, which was used by Wiesenfeld, for example, in his study. And so for that, we recalculated the same cross-section using this approximation, and we simply represent here the ratio between the exact close coupling calculation and the approximate value. And on the upper panel, it is the ratio of the global bending relaxation cross-section, and on the lower panel, it is the state-to-state. This is the reason why you have so many curves there, and here only one. Okay. And if you have a look at the state-to-state cross-section, which are usually needed in astrochemical model, well, so right, of course, we see that the ratio is ranging between 0.7 to 1.4. Sorry, I'm lost. It is the lower panel. From 0.4 to 2.2. And if we now do the summation and have a look at the global bending relaxation, which is this one, the ratio is a bit improved. It is between 0.7 to 1.4. But so the global error is divided by the factor 2, but it is still not a good approximation. So in conclusion, I would say that for collision energy associated with the region of the well, the bending relaxation is controlled by a near-resonant energy transfer mechanism. For the collision with para H2, the bending relaxation is larger towards the most excited final open rotational level, J2 equal 4, and decrease monotonously when J2 decreases. And for collision with R2H2, this is a J2 equals 3 final channel, which dominates as a J2 equals 5 level is closed for several initial water levels. And the Boltzmann weights make the contribution of the collision with H2, J2 equals 1 and 2 almost negligible at low and moderate temperature. So knowing that these calculations are very, very heavy, so it's relatively good news. At a very good approximation, a 10% error of the global bending relaxation rate can be obtained by considering the process to be controlled by the collision with para H2 in this temperature interval. And the bending rotation decoupling approximation is not recommended as it leads to errors that are ranging from 50 to 100%. So I am finished for this part, and I don't know if I have a few minutes more or not. Yes, because I know from discussing with the astronomer of the team that what is interesting for them is to have some simple propensity rules. So in fact, these propensity rules, we try to check them for the collision of atom asymmetric top collision in general, and using the example of the collision of neon with water and H2O. So you would tell me, well, the collision with neon, we are not very much interested in the collision with neon, but it's only to try to see this propensity rule, and we compare, in fact, with other systems which are of astrochemical interest. It's a collision with helium, and in fact, because in the crossbeam experiment in our lab, they also tried other noble gases. We did the comparison also with argon. So here for neon water, I will not spend time about the potential. And also there are some subtle difference when you do collision with the isopotolog of water, because you change, of course, the center of mass. So the potential is slightly changing. So if you have a look at the difference between neon water and neon H2O, you would say, well, okay, that's different, but not that much. But in fact, if you have a look a bit closer now, here it's another representation, you see that the shape of the barriers change from one system to the other. And this simple change has some real consequences. And here it is the same. We have represented when you expand the potential in the usual green basis set for an atom symmetric top or asymmetric top calculation. You obtain this coefficient as this radial coefficient, which are represented there, and compared for the collision of neon with water and with H2O. And so the dashed line, I see, are corresponding to H2O, and the straight line for water. So you see that in many cases, the coefficients are the same, But in some others, they are completely different. And it is the example of 1, 0 here, 1, 0 for H2O and 1, 0 for H2O. So in one case, it is repulsive, and in the other, it is attractive. Well, we first tried to see if our surface was okay, and we calculate the bound state of the complex. I will not, so it's in good agreement with what was available. I will not spend much time about that. But now, if we compare the rotational state-to-state rotational excitation for the two systems, we see that there are inversion of the dominant transition when water is replaced by H2O. For example, this condition and this condition are reversed, in fact. And as V10 is the only term contributing to this condition, and it's attractive for neon water and repulsive for neon H2O, I think we can say that it is the reason of this change. So again, we can do the same kind of analysis for the total rotational excitation, but I will not speak about that. So I think I will spend more time on propensity rules. I think it's more interesting for you. So what are these propensity rules? So the propensity rules were predicted by Miller-Alexander using the infinite order 7 approximation. And so because they used this approximation, it is valid for the higher collision energy and for excited rotational state with a low rotational energy spacing. And what he considers is what is the parity index, which is minus to the power j plus k. And in the case of water, k is simply ka plus kc. And for H2O, it is the same. And so when delta J is even, the largest cross-section is obtained when you have conservation of the parity index. And when it is odd, of course, it is when you have a change in the parity index. So it applies for delta K equals 0 transition, but it is not restrictive enough, as often several transitions fulfill the same rule and then cannot be sorted. So another important interpretation was due to Chapman, who had a look a bit more careful look at the three cases, sorry, J equal Ka greater than Kc, J equal Kc greater than Ka, and Kc approximately V equal to Ka. And it gives a physical interpretation, in fact, because in one case you have capital J, so the total angular momentum of water is along A, and here it is along C, so the inertial axis, of course. And in the third case, J is along B. And as you can see, that you have a nice physical interpretation of these states. Alors, still Chapman, experimentally saw that largest cross-section are generally observed for the collision with water. For delta Ka first equal J, and then delta Kc equal G, and then the third one. Unfortunately, these propensity rules are often not completely independent of the system, and are even system dependent. So here, that's what we obtain for the collision that we have had a look at, of the collision of water. So for the collision of water, in fact, we obtain some really straightforward propensity rules, but for the collision with D2O, it doesn't work as easily. But I recommend you to have a look at these papers if you are interested in these propensity rules. And I think I'm a bit running out of time now.
Yeah, 5 more minutes.
Yes, so I stop here. So system propensity rules are valid at lower collision energy and are obtained for helium water and neon water. And they are also, we check that, so they are also valid for the collision with hydrogen and for the collision with argon. So we have some nice propensity. The cross-section decreases monotonously when delta K or delta J increases. And the largest cross-section is obtained for delta Ka equals delta Kc equals 1, when several conditions are associated with the same value of delta K and delta J. This condition takes the lead at higher collision energy, and this rule also apply, as I say, for the other collision with other noble gases. Unfortunately, this rule cannot be extended for the collision with D2O, that we are still trying to understand a bit better. And I will stop with that and thank you for your attention.
All right, thank you. Any question to our speaker? Go ahead, Jill.
So you have one experimental point.
Yes,
The
that's
precious one,
unfortunate.
the precious one. So it's 300 Kelvin, you said?
Yes.
So tell me a little bit, so this is not my field, right, but what's the difficulty to get this? You have to shoot a beam of H and the beam of H2O and then hope for collisions?
Yeah, so this one was not made in a crossbeam experiment. I'm not pretty sure about it, but because it's a relatively old experiment, but it was not a crossbeam. But at the moment, effectively, Astrid Berger is trying to do the crossbeam experiment. Well, you need a lot of lasers, of course.
So to try to see the collisions, basically?
Yeah, and also the signal, of course, is quite small. So she managed to see collisions. So we have one paper, but only for rotational state-to-state transition at very low collision energy, which is at the moment published online.
So if they collide at higher energy, it's even more difficult to see them?
Depends. Well, in a crossbeam experiment, just forget it, yes. At higher energy, yes.
Okay.
Because you have the velocity spread, and all these problems. So no. So in other kind of experiment, you could probably see it. That's what is trying, for example, Jan Sims with sheared pulse experiments, at least for rotational inelastic transition. I'm not aware of any measurement for vibration inelastic.
Okay, this is interesting. So you have like one point and it has an arrow bar.
Yeah, so.
And then, well, because, and then you're saying, our calculations are not far.
Yeah.
Which is true, it's 10 to the minus 12.
Yeah.
But it's very difficult to.
Yes,
right?
No, of course, we need more experiments.
Yeah, okay.
I agree. And so that's what Astrid is trying to do. And I hope we will have some results. In fact, we also did some comparison this time for the collision with, by the way, there is something that I didn't say that I should have said, is that we did first some calculation some time ago, considering H2 as an atom, thinking that para H2 could be, but in fact, as you saw, the main contribution of to bending relaxation is due to excited level H2. So because of that, we were far, even if there was only a single experimental point, we were 2 orders of magnitude smaller.
So
So
previous models were somewhere else.
yes,
Okay.
yes.
All right, congratulations.
But yeah, of course, we need a lot more. But for the collision of water with atoms, there are a few data, and we compared the collision with argon, with helium, and I think there were also, so at least, yeah, no, for bending relaxation, there were only this one. And the agreement, again, there are more points, is not bad. It's not as good as that, but it's not bad. But all these measurements are very, very old. So we hope that, I think at the moment, some people get interested because vibrational excitation is more interesting now because of the JWST, for example, and so we hope that there will be more work.
That is my next question, but I don't want to hijack the question session, but is just for astronomers this is interesting, or is it like other applications?
Other application?
Like would the funding only come out of interest to understand
Yeah,
astronomy?
yes, only from that.
That's why there's old measurements.
Yeah.
Okay.
Yeah.
Thanks.
I just want to make sure I'm understanding correctly. So this fourth bullet point here, where we're saying that this delta K condition, delta K equal to 1 condition, is taking the lead at higher collisional energies, is that pretty much just like a restatement of the third bullet point? Because in this energy range, we would have all of our transitions open between the different bending moments for like same K transitions. Do you understand my question?
No, I think I
Okay,
didn't
so-
follow.
Like third bullet point is saying you'll get the highest contribution to cross section from delta Ka and delta Kc equals 1 transitions
Yeah, yeah.
in same mode transitions, right?
Mhm.
So then the fourth bullet point is saying in higher collisional energies, this contribution takes the lead. Is that because all of these transitions are open for same K, or is there some other mechanism that causes these delta K equal 1 transitions to take the
So
lead?
what I could answer very, well, it's a bit easy to answer that. But if you have a look at the matrix element of the potential, the angular part of the matrix element, you see immediately that they decrease with delta J and delta K. That's simple. So that's not really physical, but it makes sense at least. So now, trying to understand a bit better what it physically means, yeah, it's still to do.
I have 2 questions, technical and more general. Maybe I start with the technical. You, in the first part of your presentation, you consider collisions of H2 with H2, or just for the bending transitions, right, of H2, so neglecting. So is it the distance, the stretching distances are fixed, or it is?
No.
Or is it just
Yeah, we took into account, of course, because we are,
Okay, just okay.
they are capable, yeah, of course.
Okay,
Yes.
so answer.
So there is an iteration which is done, yeah. But
why are you interested only in the bending? So is there not, it's kind of, it's related to my second question, which is more general. If you could comment on the relevance to the observations, the astronomy observation, why I mean, what is the interest of this
Well,
data?
to be honest, of course, the lowest vibrational frequency is the band frequency. So for theoreticians, the calculations are easier than if we take into account stretching frequency, which are higher. But effectively, for water, it is known that the excitation of two quantum of the bending mode are coupled with the stretching and the stretch and antisymmetric stretch. So if we want to be able to reproduce that, of course, we will need to do the calculation with the stretch and the antisymmetric stretch. And that was the first step, which already was heavy. And so what we are doing at the moment is to, so that's close coupling calculation. But what we do now, we are coding the couple state approximation to be able to reduce the basis set and to be able to make the calculation with stretching as well. But of course, if we want to make calculation of interest for astronomers, we need that. That's sure.
And the idea is because these transitions, vibrationally excited states are observed, right, in this star forming regions.
So we are.
No, they are observed these transitions. The astronomers see these transitions from the
Yes.
vibration. This is the reason why you are doing these calculations, right?
Yeah,
to have the perceptions for excitations. And the idea that they are created by collision. So what is the process to excite the vibration?
To excite the vibration. It's most probably radiative.
Okay.
Yeah. Most probably because it's in regions where and also the temperature also is high. So that's maybe also collisional. But yeah, it's a competition between the two, and I think only models will tell.
You get a certain spectrum in the radio at certain frequencies, and you're like with the propensity rules are going to be able to say what, like there's collisions between, there's water, first of all.
Yeah, water with rare gases,
Okay,
the
the
propensity
presence
rules,
of it.
they work.
Okay. So just the presence or also the quantity or like the number of collisions happening?
What do you mean? Sorry.
Well, so what do the propensity rules produce information wise? So along the lines of what?
So the point is that, in fact, the calculation, they are possible to perform in some narrow energy interval, also including a limited basis set. And so what people like Alexandre Faure do is that they try to extend this calculation, use this calculation, using propensity rule for other conditions. And they use some kind of extrapolation, at higher energy or for more excited levels. So they ask for this kind of information because they put them in their model.
Okay.
And for example, before we did this calculation, they were thinking that the propensity rule for vibrational de-excitation were not very different from the one for rotational de-excitation. So they were coupling using the lowest delta J rule, which is absolutely not true, in fact. So it may be useful.
Into the models, they then they are able to map the sky for the presence of these gases,
So they are rather using the model
Yes.
to say what are the physical conditions.
I see.
Yeah.
So the temperature, the pressure.
Yes, yeah. And if
Is
there
that-
is-
Okay, yeah. Thanks.
All right. Looks like that's all the questions we have. All right, thank you again.